getting started. So as you can see, firstly, uh, in the last workshop, like we had seen, uh, it looks very similar to fuzz tests, but there are a lot of differences between formal verification and fuzz testing. So uh, to briefly tell the biggest difference, so fuzz testing is like it checks random, it randomly takes the uh, inputs for the functions, and it iterates over that, and uh, if if there is any violation, or then it outputs the it fails, it outputs the whether it has passed or not. But the formal verification is a bit different from that. Formal verification checks for the um, entire range. So it's not like it randomly uh, takes limited inputs. It just goes over the entire range. And you can think of it like somehow we are mathematically um, representing the inputs directly and checking whether certain assertions are being followed or not. So, uh, so you can think of it like if you, so both are important. It's not like uh, you can go only for formal verification or first testing, but if formal verification is done properly, then it can be more powerful in that sense. So um, as you can see, first we need to install Halmos. So um, there is a little GitHub repository. So here you can see first we have to install it. If anyone is running Mac, then there is this some commands which can help you to add it in the path and so on. So we will directly get into the setup, how setup is done. So we can write the setup function in which each test is executed beforehand. So uh, this is kind of like the before, in which we can access uh, the initialized contracts for the rest of the tests. So uh, you can create these symbols using Halmos cheat codes. So we'll look at what it is. So here we can see there is something called SVM create. So this is actually a cheat code which generates a symbol for uint 256. So why do we need that here? So as I said before, the formal verification checks for an entire range. So here you can see there is this svm.create uint 256 would be representing all the integers between 0 to 2 raised to 256 minus 1, rather than just being a random value between this. And you can check whether the tests have passed or not based on this. So these are the cheat codes. So if we look at the cheat codes here, we will see that, yeah, let's check out the repository svm. Yeah, you can see that just like for uint 256, the cheat code is also for create int 256, and so on. So you can think of like for each of them, it represents the entire range of all the possible values that it takes. So that's the thing here. And by the way, this is open source as far as I remember. Yeah, this tool. Um, is
Yeah, I wanted to ask,
yeah.
wouldn't that be too inefficient to like iterate over all the possible values of address or UIN 256?
Um, See, how the symbolic testing works is that uh, it it does not actually iterate over all of them. Um, we need to dive a bit deeper into that to understand, but it's something you can say like a mathematical representation. So, for example, if you want to see if x plus 0 equals to 0 or greater than 0, so if you know the properties of x, it becomes easier to uh, check whether x plus 0 will be equals to x or not. Did you get what I'm trying to say?
Yeah, got it. So it's like iterating over some subset rather than universal set.
Yeah, you can think of it. So, this is exactly what they covered in the next part. Uh, we will come to that. So, yeah, here you can see uh, we are checking the transfer between these two addresses with a certain amount. Okay. Now, the sender and receiver addresses can obviously take any value between 0 and the highest value for the address. And obviously amount is and a UN 256. So here conceptually each symbolic test is like replacing each of this symbol with a value which is iterating over all the possible values between 0 address and the highest address value. So it's like you can see here it's iterating the sender as well as receiver to the type of uint 160.max, which is this value, and it loops. There are 3 loops for this. So instead of actually writing in this certain way, the Halmos tool actually uh, kind of, you can say, it uh, what was the word, it makes our task easier. The performance and everything, you can say, is what Halmos takes care of through formal verification, and we just need to use these cheat codes for that. So are you getting what I'm trying to say? Yeah, you can interrupt me if you want. Yeah.
Okay, I'm sorry, but
Mhm.
what I understand from symbolic execution is that it translates, your function to a mathematical equation, and then we are supposed to enter some kind of invariant, or in application cases, like not specifically smart contracts. It's basically, if the application, it basically checks when the application is gonna um fail,
Mhm.
and it realizes, okay, what are the inputs that are gonna make it fail. So
Mhm.
so what my question here is, like, does it actually loop? Like, because if this example you just showed me, like, does it actually loop over all these
Yeah, correct. That
values?
So that's a good question. So the initial part is correct what you said, but what I don't think it actually iterates over all these values. It just does the representation in the mathematical form. But I think that the Halmos team here is trying to just uh, give us an example to imagine, like how to imagine what exactly would be happening. So I think that's the language they are trying to explain us here in a much more accessible way to all the developers and so on. But it actually happens in the mathematical way, like as we had seen during the Certura. Uh, if there is invariants, like the properties which we write, and if any violation is there in the form of mathematical in a way, then it takes the certain value which satisfies that or violates that mathematical equation, and it outputs that. So am I making any sense?
Yes, yes. If we go to the window, the other window, I guess yes. Now I get it. Thank you. I think this is demonstration, just demonstration. Yeah, he's saying yeah, like conceptual effect of symbolic test, but it's not happening actually.
Yeah,
I think so.
yeah. So they have used this word conceptually. Uh,
I get it now.
so it's analogous to in other words, it's analogous to running an extensive loop. So you can think of it like there can be certain sorting algorithms, and some of them have big O of n, or some of them have big O of like it can go exponential time. So what to formal verification is like it reduces to big O of log n, something like that. Like again, to conceptually understand. So yeah. So shall we move forward, or do you have any doubts again? I guess no. Okay. So yeah. So as we can see here, we have seen that it we can write a check transfer, which uh, uh, which we can use to represent the values between 0 and the largest value here. And you can see here that similarly it's for the bytes, and it's for create UN256 value as well. So here you can see there is a certain note here that for dynamically sized arrays including bytes and string to be given with a fixed size, thus they cannot be declared as input parameters but need to be programmatically constructed. So so how much I can understand is that for all the dynamically sized arrays, you need to explicitly use these kind of representation for doing the formal verification here. Okay. So yeah, let's move on. Yeah, you can just interrupt me if you have any doubts. Yeah. So uh, s- so you can see here that uh, we can use the assume feature, which the foundry has, to filter out certain conditions. So for example, if we know that the like just like first test that these conditions are not possible, or these conditions have been taken care of, then we will tell the formal verification tool that you need to not consider those conditions, or you can see that assume conditions are the input combinations that don't satisfy the assume conditions are disregarded. So for example, we know that receiver cannot be a 0 address, so we will write vm.assume receiver is not equals to address 0. And if we know that the sender in this particular function, so I guess this is the same function they are trying to explain here. So if the sender always has a token balance greater than amount, so we will just write this during writing the test. So another reason why we write this is because you can think of like formal verification tool is kind of a bit dumb tool. It is not something which can think of like uh, it will just wherever the input values violate, it will just flag and give you a counter example. So you need to explicitly tell the tool that you don't have to consider these conditions, or else it will give you false positive or something. So um, but here we need to be careful again, because we don't need to we don't want to put too much strong conditions so that we filter out something which was actually was violating uh, the invariant. So for example, let's say that there is a possibility in which the token balance of the sender is less than amount, and there is an invariant which can violate this check transfer, or which can exploit this check transfer. So if you are writing this, but somehow you are already telling that no, the balance of the no, the attack is not possible if the balance of the sender is greater than equal to amount. So the tool will never check that scenario, or give you it will never give you the counter example in which the sender is having balance less than an amount and the attack is possible. So here you need to be very careful while writing the valid inputs. So which kind of valid inputs you give is important here. So did you get it, or do you have any doubts here? So it's similar to what first testings you had done before.
One doubt.
Okay.
In first testing, we use require statement to guide our fuzzer to go in the right direction. So here we are using assume, vm.assume. How is it different from what we do traditionally in first testing?
Honestly, I guess um, uh, more than me, Mahmoud would be the right guy to answer that, because I have not really done too much fuzz testing with Foundry. Uh, but you can think of like vm.assume is something you are using while writing the tests. Okay, you are not require is something which we are writing in the code. But I think like Mohammed, if you want, you can, if you have the answer later.
Yeah. I assume actually when fuzzing, for example, you are determining runs, like 50,000 or whatever, right?
Yeah.
So if you put require, so you can imagine like a lot of inputs will be counting into that run.
Yeah.
While assume, I think is excluding it, but I need to make sure of that. But I think this is the reason.
Yeah, so Echidna is a tool for fuzzy, and it uses something which, like, if that require is a hit, it won't be using those values for the next, like, next input. So, first test will be like going against the require statement, but after that, it will be in the right direction. So, yeah.
Yes, Echidna is kind of actually different in a way that it's more smart. It have this purpose, I guess, or something like that guides it towards uh, it's that kind of reinforcement learning, so to speak, you know?
Yeah.
I don't remember. It gets it like it has a target basically to get the most path or depths or whatever. I forgot, to be honest. I used to be working a lot with Echidna, but not anymore.
Yeah. Okay. I got it. Like, yeah, I got the most of it.
Okay. Okay. So another thing here is that there is something called bound also. So uh, here they have told to not use bound and use vm.assume, because bound is something that tends to perform poorly. So yeah, that's something trivial here. Okay. Uh, let's moving on to the next part. So yeah, uh, while calling the target contracts, so we can use the prank. So obviously these are the cheat codes of Foundry, and we can obviously do the transfer. Uh, so yeah. Uh, so as we had seen in Certora, there can be certain revert statements, and if there is any revert that happens, then it it shows on the Certora's cloud that certain paths have reverted. But as far as I remember, but here as if you don't explicitly use a low level call, and there is something that's reverting in the actual function while calling, then it will not fail. I mean, the execution will continue for the external call, even if there is a revert that is happening uh, in those conditions. So you can see here, if your goal is to check whether the target contract reverts under the expected conditions, then a low level call must be used. So uh, this is because it will execute even if the external call fails, and it will check whether the invariant holds true or not even after the revert happens. So so it is an example here for the low level call to the transfer function, and it will return a success value which can be checked for certain conditions. So yeah, so I guess so far so good. Do you have any questions here? Okay, so moving on to the next one. Yeah, so coming on to the actual assert statements, these are the uh, assertions that we want to check whether it is holding true or not, and anything that is any inputs that are violating this will be flagged by Halmos, and they will it will give you a counter example for that. So uh, here you can see that token dot balance of sender should be equals to balance of sender minus amount, and the balance of receiver should be equal to balance of receiver plus amount, and any value for the inputs that violates this, it will flag as a counter example here. So we will see actually how it is working with a few examples. uh, so here there are a few tips they have given, that Halmos focuses solely on assertion violations, that is revert with panic, and it disregards other revert cases. So uh, if there is another kind of let's say revert happening, for example, they have told you that any inputs that trigger an overflow with this, or any input that is calling external contract call to be failed, it will uh, it will not flag. But if we want it to if we want it to flag, then we'll need to use an unchecked block and so on. So we will see examples of it as well to understand. But yeah, and there's another tip here, that if you are using an old compiler, then it does not have this uh, panic one error code, so you'll need to explicitly write this uh, for Halmos to work correctly. So you need to be careful that the latest compiler version greater than 0.8.0 is used. Otherwise, you need to write some blocks like this. Okay. So I guess this is a summary, that declaration of test input parameters, then specification of conditions, invocation of target contracts, and so on. And yeah, let's directly jump on to the actual examples. I think that will make things much clearer. Okay. Yeah. Yeah. So let's first look at example file here. So this is a simple example contract in which they have written total price buggy, and you can check you can see that this is an unchecked block. So uh, so here obviously an overflow is possible. uh, so here they are it returns a uint 128, and here they are uh, upcasting to uint 120 and multiplying with a uint 32. So here it's kind of a buggy typecasting, and we need to so we will write test a Halmos formal verification test for this. So it's very simple. It just inherits the example contract, and it starts with this function test total price buggy, and we take the total price buggy, we call it here, and we assert that the total should be always greater than in and equal to price. So the price parameter which is there, so what total is being calculated here, so this is actually the total. So they are asserting that total should always be greater than and equals to 0. So I'll clear this, yeah, and quantity should be equals to 0. So let's run the simple test. Oops, I guess, yep. So yeah, this is passing, but this is a simple uh, foundry test. So here you can see that this is actually fuzzing in foundry. So you can check here that 256 runs are done here, and uh, it has passed. So there is no violation that's being reported here by the fuzzing of foundry. But now we will try Halmos, the same function, and we'll see that, okay, it timed out. Okay, guess, yeah. So you can see here I ran it again, and Halmos has given us a counter example that for this kind of inputs, this assertion is being violated. So what exactly is happening here? So let's check and remix once. Okay. So here we can see the example contract. So I'm compiling this and deploying it. And let's check here that it's giving me this price value, the first parameter. I'm putting it here. Then the quantity parameter here. I'm calling it, and this is actually the total that we see here. So I'm copying this. I'm going to the Python console. Let's clear the console as well. Oops, CLS, I don't know the command, I forgot. So yeah, let's directly check that total should be greater than equals to price. So this was the total. This amount was the total. I copied it here, and it should be greater than equals to the price. So let's check the price, and yeah, false. So you can see that Halmos has successfully given us a counterexample that violates this assertion. And we counter-checked it like in Python that, yeah, this is actually, this value is actually lesser than this. That's why we are getting a false here. This value is not greater than or equals to this. So does anyone have any questions? This was the most simple example. Yeah, I think the, yeah, I guess this is, yeah, please go on.
I have one very conceptual question here.
Okay.
So how does Halmos determine which specific counterexample to provide when multiple valid counterexamples exist for a given test. Like, what is the significance of the chosen counterexample in the context?
How I have understood this. So this is again, I am telling you about what I have understood. Uh, so think of it. So I have understood it like if there is a certain violation mathematically that is happening. Uh, Now Halmos knows that uh, for this kind of range of values, there is violation of assertion happening. So it will just take a random value that lies in that range, and it will give you the value in that range which is violating. So you can see that it could have also been some it would have been even 1 and greater than equals to this, and it would have worked fine as well, right? So
It would be random or the first value of the set. Like previously, I used Jack3 solver for cryptography, and in that, it creates the like first polynomial in the set which violates uh, or the first solution.
hmm
So it would be random or the first.
uh like I think I'll need to dive deeper into how Halmos is working, because I'm I don't think I know the answer to that. So, but we need to verify how these tools actually work. We need to dive deeper into the papers on which these have been built and how exactly their code is working, or other ways smart to the yeah.
I'm assuming, I'm not sure. Correct me if I'm wrong, but I think uh, it tries to solve like the mathematical equation you talked about, but in a backward way. So it comes from it starts from the last line of code. Like first, I think it says like I want uh, this execution to fail. So now I will take whatever in this assert and make it false. So for example, it's gonna say like, okay, I want to make this total to be less than the price. And then it comes to the line after it, before it, and try also to do this, like trying to solve the equation so that total is less than price until it reaches the input and finds out which are the inputs that provoke this execution.
I see.
Yeah. Okay.
So, is there a way to like print out the range for all those values? Like
I don't think.
like the first like the first total end with 70 and the second total ends with 71 in the previous terminal only. So is there a way to like print all those values in a
Uh,
single execution?
So I don't know. I'll need to play more with this and find out if there is. So I have played a bit more with the Sartora's tool. So what I remember from there is, uh, I think the first value which it violates or something. I'm still not sure, but that was a very good question. That whether it gives the first value it violates or anything from the range. But as far as I remember from the Certora tool, uh, it gives you a specific value. Let's say there is an assertion violation, and it gives you a certain counterexample uh, every time you run the tool. But
Uh,
uh, if you want to randomize the counterexample, you want other values to get printed, you need to use another command. You need to use a specific flag, and then it gives you different counterexamples.
got it.
Yeah.
Yeah. So, like in a fuzzing, we have a seed value as well, which randomize the input. So, every time I run a fuzz test, it prints out different output, but it lies in the same range. So, that was my question, and like I got it. Like in terms of formal verification, it
Mm-hmm.
prints that maybe the first was some certain value.
Mm-hmm.
I
Okay. Okay. Yeah. I'm happy that you got the answer to your question. Thank you. Yeah. So, shall we move on? Okay. Uh, so yeah. Uh, let's see this at the end. Let's go to the more simpler examples. So there's another thing called Halmos sandbox. Uh, so here you can see this first which test we ran was on simple examples. So there are more examples which you can try out here. So um, here you can see in the examples there are other examples as well for ERC20 tokens, ERC721 tokens, and so on. And Halmos sandbox is something a bit different as well. So yeah, let's check out Halmos sandbox. So okay, yeah, let's check out the power of 2. Yeah, so here there is a certain function written in this test 2 in which they have an unchecked block here, and they are returning x, and x minus 1 equals to 0. They are ending with x minus 1. So there is a certain underflow bug that is there here, and uh, let's directly run the test and see what is the bug exactly. So yeah, uh, I'll tell you why exactly we use this loop, but just hold on for now that we are using this for this particular test. Uh, Here we see that it gives you the counterexample as 0. So if we use 0 here, so yeah, I've not told you the assertion. So yeah, the assertion is that you are running is power of 2 slow and is power of 2 fast buggy. These two functions you are calling, and then you are asserting that the values written from both of these is equal. So the power of 2, as far as I can see, is calculating the powers of 2, and you're checking that obviously when we are calculating the powers of 2, the values should be equal, uh, even if we calculate it in any way. So here the Halmos the Halmos has given 0 as the assertion violation. So why? So if we use 0 in this buggy function, we can see that 0 minus 1 here is where underflow will happen, and we are ending it with 0, but here as the underflow happens, uh, this will not be equal here anymore. So that's why it gives you a counterexample here. uh, that's pretty simple. Do you have any questions here? So I'll get on to this uh, loop here. So first let's check the loop. So here we are first checking fast OK. So here we are checking that is power of 2 slow and is power of 2 fast. The two methods to calculate the powers of 2, whether they are equal or not. When we check this, so obviously as the test sees, uh, it gives you as passed, but it gives you that the paths have not been fully explored, as the bound uh, the default bound for the Halmos is 2, and all the paths have not been explored. So if for the next test, if we run with loop 256, then we will probably get the counterexample if there is any violation. And no, there's no violation, so you can see that it has been passed. So that was kind of expected because there is no bug in these two functions. Uh, if we run the buggy function, the test without the flag, again it passes, and the Halmos itself, it tells you that all paths have not been fully explored. So use the flag. So here again we will be forced to increase the loop size, and we'll get the counterexample. And if we check what exactly is the loop, sorry, almost help. We check that is the set loop unrolling bounds, and for which the default is 2. So you can think of it like the looping, so till which it checks for the values. So I have not got much information on this here, but uh, yeah, this is how this tool is working. Do you have any questions here? I don't think we can call it max depth here as depth. So there's something another flag for the depth. But if anyone is able to come up with more information, I would be glad to hear that.
I have a question, if you don't mind.
Yeah.
I'm thinking about something you told us in Sortura, work before net, which is gonna be the thing that actually useful in our work. Is how to basically when we are working auditing, there are certain like sequence of functions that you call, and you end up actually provoking or breaking something, breaking invariant or whatever. So in that sense, in Certura, I guess it was F. You just write F, and it should be calling random functions, right? Arbitrary functions in the contract, right? So, like, is there something similar for it in Halmos? I know we can actually do it. Like, I can basically create random, create the selectors and make it as an input, and call these selectors in a random way. But I mean, like, is it already there in Halmos somehow?
This thing, we will see that there is something similar here, in which it randomly calls any of the function, and it checks whether the assertion has been violated or not. But in the Halmos example, I'm talking about Halmos example itself, which will come to in this workshop itself.
Oh,
Yeah. But the thing is, I'm not very sure of the sequence of functions which we are saying. So maybe we need to explicitly put 2-3 calls. Uh, so we'll figure that out. I'm saying. So yeah.
yeah. I meant to say, like, for example, you have like 10 functions in your contract, and you're testing some. You're running Helmos against like a transfer function, but there is the fact that if there is a certain function in your contract that is called right before the transfer, it's gonna break it, and you want Helmos to figure it out. You know what I mean? Actually, I read something in your blog right now. If you can open it, in your if that selector here, like I just
Yeah.
yes, I guess it's like Certura, right? Or is this a Certura?
This is for the Sotura. This is for the Sotura.
Okay.
Yeah.
Yeah, that's what I was like asking. Like, is there something like F, but in Helmos? That's basically.
We'll see. We'll try not to compare both of them right now because we can get confused. Because these two are like very different teams and very different tools. So yeah, we will
Okay, go.
go on and let's try to figure it out. Like afterwards, we can compare then once we are down the line. But that was a good question there. Yeah, definitely we'll check that as well. So I guess it happens in one of these examples. We'll come to that. Uh, so first let's check this out. The average, yeah. So you can see in this function, in this contract, that there is an overflow that is happening here, and it is doing like uh, ending with b and then a raised to b divided by uh, a, divided by 2. Uh, so uh, let's directly run these Halmos tests. So first we are going to run the test average ignore reverts. So uh, let's directly check it out. It is asserting that average naive should be equal to average OZ. So here it is doing a plus b by 2, which is the naive one for the average. And here it is doing this bitwise operations and then taking the average here. Uh, so I guess should this have been like this, if I'm not wrong. Okay, let's check. Let's check this. Okay, so test average is reverting. So I mean it's giving out an example for this. Let's check. I guess it even gives for this as well. The right associativity, as if I'm not wrong. Yeah, it gives you a successful run this time. Again, run this. Okay, it actually ignores the revert, which happens during the overflow here. And if we call the this test with reverts, uh, so here you can see in this test we are explicitly calling the average naive and average OZ function using a low level call. So as you remember from the getting started document which we saw here, a little call, yeah, I guess this is not it. Call this, yeah. So here you can see that they tell you to call to use a low level call uh, to check if you want to check even when the target contract reverts. So here we are using a low level call and then we are asserting whether these results are actually equal or not. So here we see that we get okay, we have got a looping. Let's try with the flag of the loop. Yeah, so we get a counterexample here. So as you can see from this that if you use both of these inputs for A and B, this will actually revert. So as you can see here that we have not used an unchecked block. So as we are using a Solidity compiler version greater than 0.8.0, this, if there is an overflow, then the compiler will revert. Okay. So uh, that's why when we ran this first test, it ignores the revert and it just passes. But for the second one, if we explicitly use the low level call, it gives you the counterexample, otherwise it does not. So is this clear? Do you have any questions here? If you want, we can check this here in Python. So if we are and with, I guess, will this work or not? But yeah, I'm just wondering even if this makes sense or not to check here. But yeah, I think it's pretty much clear to you here. So let's move on to the next one. So any call low level. So here you can see uh, that the ERC20 token is having a public transfer function. So this is a very critical bug because anyone can then transfer it uh, to uh, to themselves. So we will they have written a test any call low level. So here you can see that uh, they are checking the balance of owner and they are pranking this bad guy and they are calling an arbitrary data here. So Mahmoud, as you had asked, uh, they are putting an arbitrary call to this token contract and they have pranked an attacker here, but we have not specified to Halmos as to which function we want to call. And after that, we are checking the balance afterwards of the owner and we are checking that balance before and afterwards is the same or not. So let's see what happens if we run this. Guess I should be copying from here itself. Uh,
Yeah, this is actually what I suggested about manually adding it.
yeah, exactly. Yeah. So I should have run this first. Okay, so here you can see we get a counter example here for any low level call. So let's get to the code here. Yeah. So it says that it does not find the bug, but we have seen it has flagged something. Yeah, I'm not sure about this because I just ran it before the workshop as well, and I got the same answer here. So maybe uh, they have uh, updated this tool or something with different parameters, and this is not working. But if if so they wanted to tell that if you are just using this data and then running this code, then you will not find the bug. But if you use this with a specific create svm bytes which takes a specific a range for the data, then it will generate a counterexample. So let's run this. For some reason, I'm not able to copy this. Yeah, so it will give it the same answer here. And if we check what exactly is this is nothing but the call to the transfer function, which is public one. And by calling this, it is actually able to change the balance afterwards of the owner, and due to which balance before and balance afterwards is not the same. So this is an arbitrary call of the bytes which the attacker is able to generate. So I guess uh, there is a function signature also of the transfer function here, which we will get after hashing this, if I'm not wrong. So we will see in the next example, which will be more clear than this, as to how to interpret this kind of bytes. So does anyone have any question here? Like Mahmoud, is it clear here, or do you have any more ideas here?
Yes, yes, it's very, very cool read. I like it.
Okay, great. Yeah. Okay. So if you don't have any questions, let's go to the next example. Uh, So now this is the call to the symbolic address, and it's the 13 file. Okay. So this is a very simple test which we are writing. So we are assuming that so first let's see the recipient. So there is a parameter called recipient address here. Now we are assigning a specific address as the target address here, and we are setting the balance, like we are assuming that the balance of target is 0 initially, and we are giving 1 ether to this address, which means the contract. So the contract has 1 ether at the start, and then we are sending 1 ether to the recipient. So uh, after sending this 1 ether to a recipient, which we don't know, which can be any address here, we are just asserting that the balance of the target should be 0 ether. Okay. So let's say this is a vault. This can be a vault or something, and this is a function, and there is a recipient here, and we are just trying to check if the balance of the target should be 0 at the end, because certain calls have been made, and we are just assuming that after all these calls, the vault should be 0. Like how we are assuming that it should be ideally 0. But let's run this uh, test. Let's run this test here and check. So yeah, so this is a very simple thing, that it gives you a counterexample that if the recipient address is 0x42, then the target balance will not be 0. So what does this mean? This just means that if we are putting this address itself as the recipient, then this assertion will get violated. As simple as that. So we can say that if recipient is a target address and 1 ether is sent by the contract sends itself, you can say here, then the final balance is non-zero, because like if, we are doing an external call obviously here, but the recipient is the contract again, this address, so it will finally again have 1 ether and not 0 ether. So you can use it to check any assertions or invariants of the vault. So the next is the uh, prank call. So here we are assuming that the balance is again 0. We are saying that the sender and recipient should not be equal. So another condition we have added here, you can see that we have 2 parameters here instead of 1, which was there in the previous. and there is a sender now and recipient here now. Now we are pranking the sender, and we are giving him 1 ether, and we are transferring 1 ether to the recipient, and we are checking if the balance of the target is 0 or not. So actually I would try to come to something which we had learnt in Certora. Um, while using Certora tool, if you remember, we had learnt that uh, you actually don't need to uh, understand the code too much while doing formal verification. So it's like, if you understand what exactly is expected from the system, then you will be able to write formal verification tests. Uh, are you getting my point? So it's like, whatever be the code, I am not concerned about the code. I am trying to build a system which represents, which my code is going to represent, and I want certain things to be true uh, in this system. I want certain things to be true in my code. The code is something I don't know, but I know the properties or the invariants which this system should be holding, and based on that, we are uh, writing some preconditions, and we are actually carrying out some things here, and then we are checking whether the assertion is holding true or not. So if on a high level you understand the code, I think you will be able to write formal verification. So this is kind of uh, something which I remembered, uh, which can help while writing formal verification tests for Halmos. So here directly let's run the test again. So yes, that should have been dash. Yeah, so you can see, you get a counterexample right away that if the recipient address is 0x42 and the sender is this address, then this does not hold true. So what exactly is happening is we are pranking the sender, and uh, he's sending 1 ether to the recipient. Then the target's balance is non-zero if the recipient itself is the target. So this time, the formal verification tool figured out that if we are putting the recipient as target here, then this assertion gets violated, because now uh, this recipient, which is the target, will have 1 ether and not 0 ether. This is very simple thing, but this can be powerful if the code is like complex and has some complex properties which it should be holding. So is this clear, or do you have any questions here?
Yeah, it's clear.
Okay, great. Yeah, let's move on to the next one then. So this is a very simple example again. You can check out other examples as well, but I'm covering which is I found most interesting, or something which we can learn from while writing this test. Uh, so here you can see that we are just asserting false here, and we are just checking how the tool behaves when we write something like this, which you must have been remembering we tried a lot during the Certora tool. Uh, as to how it behaves in certain situations. So yeah, you can see that it is giving potentially invalid this kind of symbol, and it is giving it as failed. So if you remember that this is how it behaves, it uh, kind of reverts as we had seen before, only in the panic cases, panic 1 error. So if I'm not wrong, this is a panic 1 error, and that's why it fails for this. So this is the behavior of the tool here. So yeah, let's check out the example here. Yeah, so this is own contract, handler contract, test two-step ownership. Okay, so we need to check here the stateful invariant. So um so this was which I was remaining to see actually, but you can see here that initially while testing we set up that the owner should be this address, and we are deploying this owned contract and assigning it to owned here, and now we are checking uh, that the owner of the owned should always be the owner, which is this address, and we are asserting that the owner should always be the owner of this contract, which was the one which is this address itself. uh, we should run this as well, I think, for better understanding. Okay. Execution can count in a static call. No successful path. Okay. So that was just a warning, but you can see that it passes that uh, the owner is always the owner because he is the one who deployed the contract. So you can see in the owned contract that owner is the message sender, that is the one who is deploying the contract, and you can see here that uh, this contract itself deployed the new contract, that's why it's the owner. So yeah, so they have written a funny here invariant that if invariant owner never changes, this is bad lol. So now they are checking this stateful invariant. So they are, as far as I can see, trying to call certain functions. They are using an arbitrary bytes here. Uh, then sender, they are using svm create bytes to use any address that is uh, coming in the address data structure, and they are sending the message value to the sender, pranking the sender, and now this sender is uh, doing certain low level calls on this owned contract. And here exactly we are checking, okay, this was the invariant that this never changes, owner never changes. So here we can see that we are not specifying which function to call, and we are going to see that is there any call to the functions above in a certain manner. We can see here that function selectors length can be anything, right? So we are letting Halmos to actually call any amount of functions here, and we are looping over that, and we are kind of telling Halmos that you just go on and call any of these functions in any order and check whether there is any assertion violation or not, if the owner is changing or not, is what we are checking here. So let's see if it is able to find anything. So this is exactly similar to the F which we were talking about before. Uh, okay, it's running the test, and let's try to figure out if there is any violation here. Yeah, you can see here that there are two functions which Halmos is calling in certain order, in which through which you will be able to change the owner of the contract. So the owner of the contract does not remain the same if you call these two functions in this order. So which are those functions? Honestly, we need to see that. Uh, so yeah, but if you want to see which function it exactly called, we need to check the uh, function signatures here. So if you remember, function signature is nothing but a get check hash, and we are taking the selector values. So let's try to uh, calculate one, but uh, yeah, we need to check which function it has called in which order to check the violation to to see whether the violations happened, how it happened. So, do you have any questions here? I think this is pretty easy to understand.
No.
Okay. So, in the next example, we will exactly see this function selector thing. Okay. So, let's check out the final example here. Uh, I think it's becoming a bit slow. Yeah. So, the final example is of a DStable coin backdoor. So, if we check on the Rect news, this was a $6.5 million hack on Arbitrum, BSC, and Ethereum, like total amount of tokens that was lost, and the stablecoin depegged over 80%. So, what was the vulnerability? So, the vulnerability was that the in the burn forking function, the developers had actually misordered the parameters, and due to that, the attacker was able to approve the tokens to himself and drain the holders funds. So what the Halmos team has done is that they have written a certain test for demonstrating that. Let's check that out, because this is something which is more practical and interesting. So these were the simple examples, and yeah, let's directly run this. Okay, let's first check uh, the code here. Yeah, so if you can see here, uh, this is the code of the day stable coin here. LDAY they have written here, and let's check the burn function here. Yeah, and this burn from function, this vulnerability was in the burn from function. uh, you can see here that the approve function parameters were switched. So what do I mean by that? We can directly check above which is the correct code on how to use approve. So ideally you should be using message sender first, and then the spender, and then give certain allowance. But here the developers got smart, and they just switched it here, and they give this parameter as the second one and spender as the first one, which is the account here. And as you can see, this is problematic. Why? Because let's say that there is certain current allowance which message sender can give to any account. So let's say I am an attacker, and uh, I used the approve function initially. Before burn from function, I had approved Bob for certain amount. Let's say I approved Bob for say 1,000 tokens for now, and you can see that current allowance which I have given to Bob will be 1,000 here. Now what I can do here is I can put Bob's address here, and I'll put 1,000 amount here. Oh no, sorry, I'll put 0 amount here, and you can see here that Bob would be approving me for current allowance minus 0. So current allowance would be something which I had myself set to approve, which will be 1,000 here. So what would be happening is that I would be provoking, like Bob would be approving me for 1,000 tokens. So you can see that uh, obviously the next one is like burn of the account is 0. So no issues with this. But here the attacker can uh, approve for unlimited amount of the user itself. So yeah, do you have
Yeah.
questions?
It actually looks so bad that actually the fact that you can call burn from and you burn anybody's tokens, you know, like I mean another thing, like the function itself is weird.
Yeah, the function itself is weird. I agree with that. But it I think it is they wanted to approve. They wanted to give a feature in which I can approve certain person to burn my tokens. Maybe some use case that they come across, like they got an idea or something. So
Yeah, but I mean, yeah, anybody can burn anybody's token as well. Like I mean, like you can,
yeah,
like,
if you can transfer anyone's tokens, then you can burn. So here exactly, you are not burning. You are not be able to burn, but first you will be able to get approval of all the tokens. Then you can do anything with that. Uh, is it clear here?
yeah, yes.
Yeah.
And look, you
Okay.
know,
Okay. So uh, let's go to the example here. Yeah. So uh, you can see this is the actual test that these guys have written. So um, you can see here in the setup they have used this bytecode. This is the contracts bytecode that they have directly copied, and they used the DStable coins interface directly here. So they have got the code and the functions of this contract. So they didn't write everything here. They just got this bytecode and this interface. And now comes the interesting part. So, as far as I can see, as I can remember, what they are doing is they are trying to set up here the initial values for the token, and after that they are assigning, like taking 3 holders here, and they are creating the balance and amount and pranking a certain account here, and they are trying to check whether there is any certain kind of backdoor here or not. So uh, I guess this is kind of the any range of values. This is trying to say that uh, the token will be transferring any amount of uh, uh, balance to these holders which are there here, and they are it's approving these holders. So for the amount, for any amount, and now they are this if statements, as far as I can see, is something which is code specific, and this is something like vm.assume, if I'm not wrong. They are trying to filter out certain conditions which this token is having in the code. So right now actually I forgot which was that uh, because it was about a week since I had checked this. But you can assume for now that this is something that they're trying to filter out here, and then they are taking this as a certain arguments, here. They are trying to randomly call a function and they are checking if there is any backdoor here or not. So what is this check no backdoor? So if you will see, this is something more complicated, a bit complicated. So uh, they have actually written a specific ERC20 test which actually checks whether transfers are happening properly or not, whether transfer from is happening properly or not, whether the properties and assertions, the invariants are holding or not. And similarly, they have written certain conditions in which they are asserting that uh, the caller cannot spend other tokens without approvals. So here you can see that uh, there is a selector here, there is an argument here, there is a caller here, and there is other here. So we will need to be a bit more brainstorming will be needed, and we need to be smart while writing these kind of tests to figure out these kind of bugs. But you can see here the gist of it is there is like pranking of the caller, and you are arbitrarily calling a function, and then you're asserting that the old allowance, if the new balance of other is less than old balance of other, the old allowance should be greater than equals to the subtraction of these balances. So this is another way of saying that you cannot spend the tokens of others without their approvals. So uh, without diving too much deeper, we'll directly run the test here. Yes, we can take it from here as well. Yeah. Uh, yes, that is here. Okay, so there is this thing that actually running this dash dash function and then the function name. So actually it is checking for other tests as well in which this function has been called. So this is not the most efficient way. You should ideally be using a dash dash test as well for this. But if your test names are different, then you don't need to worry about some other test running along with this. But I would let this run for now. Yeah, till that time, if you have any questions, you can ask regarding this. Uh, because this is something a little that is a bit complex. So for understanding this, we'll need to dive a bit deeper into this, but I guess it's quite a lot of time now.
I would have said like this needs its own workshop.
Yeah,
Yeah,
kind of.
seriously.
Kind of, yeah. So I guess
I think it can be really good.
if we
Because we can reuse these tests, right, in our projects. I mean,
yeah, yeah, you
that
can.
ERC 20 test, I think it can be useful.
Yeah, I guess yes, you can do that for the transfer and transfer from. Yeah, should be faster. Okay, so this one passed. So there was no backdoor in this curve token. So which is the curve v3 token, which is this token. So there is no such kind of backdoor here. You can see here there is certain different conditions given here to check whether there is a backdoor or not. And so this is the test for DStable coin. Yeah, and we can see we got a very big and beautiful counterexample. So the gist of it is like obviously here if we will see in the test, so Halmos is trying to give us these three different parameters, the values for this, and what is most important here according to me is which function it is trying to call here. So uh, as we know that the problem was in the burn from function here. Yeah, the burn from function. So Halmos has actually figured out which function actually violates the invariant, and it is giving this selector here. So let's just quickly check the selector this time. For that, we just deployed uh, a function selector contract in which it is nothing but it giving the selector of this function. So going from function, it will not work like this because as you know, we need the complete parameters for that. So yeah, so the signature hash of this function. Wait a minute. Yeah. So I'm copying this and putting it in remix here, and I'm putting it as a string here and calling this. And you can see this is 79cc6790. So 79cc here, and you can see that this is the exact function that Halmos figured out to call in order to uh, check if it violated or not. And as you can see, these are other values. You can check for that as well, but this is what I think is the most important one. Yeah. So I guess this is where the workshop ends. If you have any questions, you can ask. Otherwise, I think yeah. So guys, do you have any questions here?
I mean, I don't have any question, but I was just thinking, like, using this tool or any other formal verification tool, right, for the audit, it could be such a time consuming, thing, along with the manual auditing part. So I was just thinking, like, how should we, plan?
Yeah, that's something we need to discuss with
Mhm. Yeah. So what I was thinking first is like if we are able to figure out to use this tool on the previous audits, maybe we will be able to get uh, a hang of how much time it takes to use the tool, and we can then use that to decide if anyone should work on this tool or not. Uh, did you get what I'm trying to say?
Yeah, Kuldit is right. I think we need more time.
Yeah.
We just tell them we need more time for it.
Yeah, exactly. We will not be able to right away write kind of these tests for the big code, I think. But if we are able to find the same bugs we have found out in the previous audits, maybe we'll be able to get a hang of it faster. Which was an idea which I got while using this tool. Yeah.
Because the last audit that we did, right, on Met Exchange, so that was just mathematical formulas that we had to validate. and this would have been very much helpful for that scenario. Feel like when they were casting values.
Mm-hmm. Yeah.
Yeah.
Yeah, exactly. So in this Wombat audit, there were a lot of libraries. So I mean, the two main libraries. So if you will check that the examples that Halmos has given, so yeah, it works pretty well. It is a good choice for to use on libraries. So that's a very good point there. Yeah. So you can check in the uh, and these examples that they have used it on a lot of libraries, mathematical libraries.
Yeah. I think Echidna also does the same.
Yeah. Yeah. Yeah, true. So the thing is like if one thing is if you are able to write first test in Foundry, so that same thing you will be able to use for forward verification here. Yeah. Like the simple tests I'm talking about. Okay. Yeah. Yeah. So I guess that's pretty much it.
I mean, like share the GitHub repo channel.
Yeah, yeah. I'll send all of them, all of it in that channel. Yeah.
Ishwar. Thank you.